Like we saw in substitution, there are two ways we can approach elimination. We can either do everything in one step and abstract the proton, creating the double bond and forcing the leaving group off, or the leaving group can leave first, allowing us to fill the hole by abstracting a proton to make the double bond. The one-step mechanism, or the concerted process, is E2, and that's what we'll start with here. So considering that the generalized idea is that we're going to abstract a beta proton, its electrons are going to become free to form the double bond, will form the double bond, and that will force the leaving group off. So now we want to consider, that helps us figure out who our players are, the important parts. Well, we discussed that beta protons are one of them, which would be, I'll just draw one on each of the two spots, because these two spots are different. We have two different types of beta protons here. Also, we'll be forming the double bond somewhere between either, here or here. And then the last thing we want to consider, our last important player, is the leaving group. And here, something should be standing out. If we think about substitution, we should realize that OH as a leaving group is a bad leaving group. It's unstable when we kick it off. It's not nearly as stable as its analogous molecule water. So we want to consider, okay, and we have our base here, which, if another way to draw that out, the terpbutoxide is like this. So we have our base, we have our beta protons, we know we're going to form, but our leaving group is still bad. Well, if we remember from the substitution section, we can convert this OH into a better leaving group by using tosyl chloride and pyrimidine. So when I write the molecule again down here, the same parts, but our OH group will be converted to a tosylate group, which is OTS. One thing to notice in this problem is that we're disregarding stereochemistry, and we'll look at them more closely in one of the next few videos. Now that we actually have a great leaving group, this guy checks out to leave. It's going to be a stable leaving group. We can now look at the mechanism that we're going to use to actually achieve the elimination. So if I redraw my base over here, the terpbutoxide, we know it's going to abstract one of two protons, one of the two beta protons that we drew up above. But the question is, which one? Considering the size of our base, the fact that it has 3 methyl groups attached to the carbon, the central carbon, it occupies quite a bit of space, which means it's going to be harder for it to reach this proton as compared to this one. So what's going to happen is we're going to abstract this proton. Its electrons are going to come down to form the double bond, pushing off the leaving group. So as I redraw that, I'll put this, have our aromatic group, and that's our product. Now your specificity for preference for abstracting this proton over here, we'll look at more closely in one of our later videos. But considering that we had a bulky base, the steric hindrance that we achieved allowed us to prefer the beta proton on the right compared to the one on the left. And we refer to this product that we call as actually the Hofmann product, meaning the actual less substituted product. Of course, we also get the other product because it's not specific, we're just getting a preference. So if I redraw this, if we were to abstract the other proton, we would have done this product, which is the more substituted product, and that would be the Zaitsev product. And once again, we'll look at this more closely in one of our other videos.